hypothesis, and I'm of course going to back this up in a second, is that we can probably move all this stuff to the edge, and it'll be 4 to 5 orders of magnitude less parameters. Everybody will have their own private LLM and maybe 5 of them. And if you just want to look into history, you will find out that this is what happened, right? Remember IBM was saying we can maybe sell 6 computers? And if you know UC Berkeley, Corey Hall was built with higher ceilings because they thought they have to put big computers in. Turns out nowadays, my cell phone has way more power than any of the computers that they want to put in Corey Hall. And we know this story, all of us. And we think history won't repeat. I think it will, okay? And maybe I can have you join me in the thought that history will repeat. Now, why do I say this? I can back this up with fundamentals. On that note, what did we used to do to compress data? You know, gzip, all of this stuff. What's behind that? Information theory. So what can we do to compress models? Information theory, okay? So the interesting part here is, my book is coming out, Halloween 2023, Information-Based Machine Learning. And I taught this class for years at UC Berkeley as experimental design for machine learning, because it turns out you can show a bunch of stuff of how we are actually splurging neurons, right? We just use billions of neurons where we could use a lot less. And in order to show you this right now, I invite you to come with me on a journey on the whiteboard to just show one simple proof that we, you know, with a little bit of background, I hope that we all have, will understand. It's a mathematical proof that we only need a logarithm of the number of instances amount of neurons for binary classification. In fact, less than that, the logarithm is the upper limit. So if you had 10,000 instances, the logarithm of that, obviously log 2 of that is, as we know, maybe gotta do the math right now, but something like 13, 14 bits, right? So you would only need 13, 14 neurons. Let's take a look at that. So what we have always, and this is how I normalize any data that we ever look at. Remember, we're doing automatic machine learning, right? We're not treating, so the automatic machine learning is like this. Remember how arithmetic is solved in a computer automatically different than we would solve arithmetic as humans, right? Convert it to the binary system, for example. Well, AutoML is similar. We don't care how humans do it. We do it in a computer completely automatically, and we have to create different techniques that make it automatic. So what we have always is a table. It looks like this, okay? It has D dimensions. It could be age, gender, social status, had COVID, right? And then you have some function, which is your labeling, right? Looks like this. And for now, just for fun, we'll make those labels just, binary. And we make it such that these labels are uniformly distributed, okay? So the probability of 1 is the probability of 0, okay? So we have some binary classification function. Some binary classification function, okay? And it turns out, I don't even care about the dimensionality here, because what a neuron does, as we all know, maybe, hopefully, is that it will calculate the dot product and will ask itself, is the dot product greater than a threshold? And if so, that is obviously, oops, it's hard to write here. That is obviously my f of x, right? And I obviously goes from 1 to d, right? That's how a neuron works. It's a threshold. And if above the threshold, it's a 1, and if it's below a threshold, it's a 0. Now you have an activation function on top of it, you will see we don't need it. So what happens next? Let's assume I create a neuron that's completely randomly initialized. I don't train it. I decide not to train it, okay? So it looks like this, right? It's a neuron. There's x1 as an input, w1 here, w1 here, and so on, until it's xd. and it's WD here, right? All goes in here. There's a neuron. And these WD, for now, will be, or this WI actually, will be random. We use math.random. It's nice and fast. What is the accuracy, the expected accuracy of that neuron? If you now measured the f of x dash that comes out here, what comes out here, right, is f of x head, right? How often will f of x head be f of x? Pick a guess. Once? No. How many? What's the percentage? Let me give you a hint. If he flips a coin, and I just say head, tails, head, 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 tails, how often will this be right? 50, somebody said it. 50% of the cases, exactly. Right? So with a completely uniformly, randomly initialized neuron, this neuron will get 50% of your data right. It's called the best guess accuracy. It is 50% because I said here that we have 50% zeros and 50% ones. Okay, it's called the best guess accuracy. So now I do the following trick. I take all the data that this neuron got right, and I create another neuron that's connected here. I also initialize it with random weights. But I only give it the data that the first neuron got wrong. How much does the second neuron get right? He said it again, a half, right. So the first neuron gets 50%, the second neuron gets 50% of the 50%. That means in total right now, between the two neurons, we have 75% right. And you can see where this goes, right? We add another neuron. How much do we get right? Well, 50% locally, but globally, 50% plus 75% plus 25% plus 12.5% is something like 87.5. And I can continue this, and we will find out that if this is n as the number of instances, that we only need log 2n neurons between the neurons to get everything right. There is a small problem, though, which I skipped over, right? The small problem is we have it right between the neurons, and we need to have a decision neuron here that finds out when something is right. Now, that is a non-trivial problem, but and of course won't work by just doing random. But here's my question before we go there. Do I need more neurons expectedly or less neurons if I don't choose random, but I train them? Less. Somebody said it completely right. So this thing is an upper limit. So what this means is we can use a lot less neurons than we all think, and this makes me think that in the future we can push stuff just on the edge, and every cell phone will have an LLM, and every robot will have one too. And again, I wrote 248 pages that come out in Halloween on that. The interesting part here is that this, then just some caveats, this is an optimality proof, right? So the point is, it doesn't tell you how to build that network, right? And so now people should ask questions of like, okay, but what happened to deep learning and why are we using so many neurons? Well, we're using so many neurons because our current training technology is backpropagation. And it's trying to sort of randomly solve a packing problem, right? This packing problem, again, of finding out which neuron is right here isn't easy, right? I just skipped over that. But the point is, why do I bring this up? Well, first of all, it's an Edge summit, and I thought I'd bring something about Edge. But the other thing is, there is actually a huge amount of untapped knowledge, if you just go back to the fundamentals, where you can start making things probably 10 times, 100 times faster. And what I learned, and without, contradicting my former panel person, is when you have something that is orders of magnitude smaller, orders of magnitude cheaper, orders of magnitude faster, you have something, and it doesn't matter so much of its distribution and all of these things. This is why, as the former panelist said, in 2005, it was much easier. It was much easier because there were big innovations like, oops, we have an internet. We have another big one, which is like LLMs. But I can tell you, you don't have to just go there. There's a lot of room left to make things small, efficient, fast, cheap, all of these things by orders of magnitude. That's actually all I wanted to say, so I'm happy to bring questions. Thank you very much. Yes?
Yeah, we have time for one question. The MVP of questions goes to this guy.
So I'm curious if deciding which neurons are right or wrong isn't moving the problem, the parameter budget from one side to the other. It might be harder to decide which neurons are good than building a big model.
So it's hard anyway, but the point is you always have to see that if you do backpropagation, you stop at a random point. You don't know if you reached the optimal at all, and most likely you didn't, because the number of states you have to go through is exponential, right? So the answer here is this is an optimality proof. Unfortunately, I wish I just had the answer of how to build that network this way. Okay? I wish. I don't. But the point is, this gives you a perspective of how small it in theory could be. And even if you're still 10 times bigger than the theory, you're going to be extremely small. Thank you so much.